Still looking at rates of change, but now how we can use integration to help us solve problems. So if we've got the rate of change, then integration will allow us to find the original quantity. So 2017, we were told the rate at which water flows into a tank to V to T is 2T on 1 plus T squared. We want to know the exact amount of water in the tank after 10 seconds. They've also told us initially the tank is empty. So we know dV to T is 2T on 1 plus T squared. Now, I'm going to use definite integrals to solve this. So remember, when you want to solve as a definite integral, we've got our derivative. I want to separate the variables and then match the limits. What this basically does is it eliminates the need to find the constant of integration. All right, so we split it up. So we get the integral of dV is equal to the integral of 2t on 1 plus t squared to t. Match the limits. Well, they said when t is equal to 0, v was equal to 0. They're my bottom limits. So at the top, we want to know 10 seconds. So when t equals 10, what is v? So I've left that as v. Okay, so let's integrate. Well, integrate the v, I just get v. And integrate 2t on 1 plus t squared, and we get the log of 1 plus t squared. Sub in, v is the log of 101 on 1, so log of 101. So there's the log of 101 litres of water left in our tank. So as I say, I didn't have to find the constant of integration for this one. The other thing to note on the left-hand side here, whenever we have something like just dV going from 0 to v, it's okay just to write v down straight away. We don't have to physically write the square brackets. Okay, let's have a look at the 2010 question. So acceleration is given by 4 cos 2t. We want to find when this particle first comes to rest. So when is v equal to 0? Well, acceleration is dv to t. Separate my variables. So integral of dv is 4 times the integral of cos 2t. Match up our limits. Now they've said when t equals 0, v equals 1. Now, we want to know when is v equal to 0. So on the top limits, I've got 0 on the dv, but t on the cos 2t. Integrate. All right. Well, again, when I integrate, I just get v. But in this case, I do need to write 1 to 0 because we need to substitute these limits in. So on the left-hand side, I'll get 0 minus 1, negative 1. Right-hand side, sub in t, we get sine 2t. Sine of 0 is 0. So we're basically solving sine of 2t is negative a half. We want the first time that happens. First time that happens is in the third quadrant. So 7 pi on 6 divided by 2, 7 pi on 12. So the first time it comes to rest is after 7 pi on 12 seconds. And we'll do this one from 2013. This was an extension question. We were told that dV to t is minus 10 to the power of negative 4 times some constant a, which is the surface area of the raindrop. We have to show that the rate of change of the radius is also a constant. So it starts off like our related rates questions. We want to find dr to t. We know dv to t. So I would now like a link between v and r. Well, we know the volume of a sphere is 4/3 pi r cubed. So dv dr is 4 pi r squared. 4 pi r squared actually happens to be the surface area of a sphere. So dv dr actually turns out to be a. So dr to t will be dv to t minus 10 to the power of negative 4a times the reciprocal of dv dr, 1 on a. The a's cancel. I get minus 10 to the power of negative 4, a constant number. So yes, the radius is decreasing at a constant rate, that rate being 10 to the power of negative 4 meters per second. So how long does it take our raindrop to evaporate? Now, our raindrop, we're saying, has a volume of 10 to the negative 6. So dr to t is minus 10 to the negative 4. We just found that out. Now, volume is 4/3 pi r cubed. What I need to do is find out what is the radius of my raindrop. They told us the volume, but I want the radius. So subbing in, we get that the radius is this beautiful expression, the cube root of 3 times 10 to the negative 6 over 4 pi. Back to our derivative. Separate the variables, and we get dr is equal to dt. Now, I've done a few things in one here. Yes, on the right-hand side, it should have been negative 10 to the negative 4 dt. But because I'm trying to find t, well, dividing by negative 10 to the negative 4 is the same as multiplying by negative 10 to the power of 4. Matching our limits. When time equals 0, we got that wonderful radius. We want to find out the time when the radius is 0. So t, I've got that situation where I'm just going from 0 to t. I can say that is t. But that's going to be 10 to the power of 4. Notice I've swapped the limits and got rid of the negative. And we're going from 0 to that wonderful expression. So subbing in, we'll get 10 to the power of 4 times that cube root. Well, let's bung that into a calculator. And that comes out to be about 62 seconds. So it takes about 62 seconds to evaporate. Okay, so 9F will finish off our look at rates of change.